Hello, so today we're presenting Parikh's theorem. Our group members are Kevin, Srisankaet, and I'm Andrew. So who is Parikh? Parikh is an Indian-American mathematician born on November 20th, 1936 in India. He's currently a professor at Brooklyn College, which is a subsidiary of the Central University of New York. And he has graduated with a PhD in mathematics as well as a PhD in physics from the Harvard University. His research mainly focuses on belief revision, logic, and game theory. So Parikh has made many contributions to his field of traditional logic, where he mostly works with things like recursion theory as well as proof theory. He has had multiple publications, with his most popular one being on context-free languages, which is where Parikh's theorem has come from. He also has other popular publications, such as the existence and feasibility in arithmetic, as well as the logic of games and its applications. So fun fact. So in October 2018, Parikh had been under fire for his controversial Facebook post discussing immigration. In his post, he said things like, Hispanics are good people, but are they really the population which America needs for the rest of the century when more and more education is required? Hispanics have the highest rate of dropping out of school, and immigration is good, but I hope someone will explain to me why Mexico is getting the lion's share. These posts have caused public outrage at Brooklyn College, the school he's teaching at, leading to two rallies. However, it seems that no significant repercussions were given to Parikh. So on to some required background information that we need for the proofs. So just to reiterate from earlier this semester on context-free languages. So context-free languages are languages generated by context-free grammars, and they're basically languages where no context is used in the rules of processing a language. And CFGs are usually defined by a for tuple, as shown on the slide here, and we have also presented an example of what CFGs are. And here we define regular languages. So regular languages are languages decided by finite automata, such as NFAs and DFAs, and they can also be generated from a regular expression. On the slide here, we see the definitions for NFAs and DFAs, and at the bottom we can see some examples of regular expressions. So now onto the actual meat of our theorem. First, we need to discuss what Parikh image is. It's also known as Parikh mapping or Parikh vector, but for here I'll just say Parikh image to keep it consistent. So basically, given a finite alphabet, sigma, and a string that's made from the characters from that alphabet, the Parikh image function is a function such that given the string, we can generate a vector of natural numbers, such that the vector contains the frequency that a character shows up in W. And then two strings are letter equivalent if their Parikh images are the exact same. So in the bottom here, you can see an example. So let's say our alphabet is A, B, C, and D. And then our word is 4 A's, 2 C's, B, D, A, D, B. Then using the Parikh image mapping function, we get the resulting vector of 5 A's, 2 B's, 2 C's, and then 2 D's. So here we would define what Parikh's theorem is. It basically says that for any context-free language, L, there is a regular language, R, such that the Parikh image mapping of L is equal to the Parikh image mapping of R. Therefore, these languages, L and R, are letter equivalent. Context-free languages are equivalent to regular languages if we ignore the order of letters in a word and only consider the number of occurrences of each character, similar to an anagram.
So after establishing all of this, let's now talk about the proof. From the papers we read, we saw that there were multiple different proof methods. The first was Parikh's original proof, which revolves around using trees and the depth of them. Then there was a strong pumping lemma proof, which was referenced in Faulkner's lecture notes as well as in other papers we saw, as well as a proof by NFA construction, which is what we will be doing today. So the goal with this proof is to show that given a CFG, which is G, which is defined by its four tuple, V, sigma, R, and S, we can construct an NFA to simulate the changes in Parikh's image happening during a derivation of G, thus showing that they are equivalent in power under psi, which is the Parikh image function. Now let's define some definitions before we go into the actual proof. So given an element alpha of V union T star, where V is the set of non-terminals and T is the set of terminals, also denoted by sigma, we denote psi V, so psi sub V of alpha, to be the Parikh image of alpha, where only the components in V are considered. Moreover, we denote A sub/V to be the projection of alpha onto V. To provide an example here, if we have V, which is our set of non-terminals, being equal to capital A and capital V, and we have T, which is our set of terminals, being equal to lowercase a, b, and c, and we have alpha equal to lowercase a, capital A, b, and then two uppercase b's, then psi V of alpha would be 1 and 2, since we can see there's one A and two B's. Well, one capital A and two capital B's. And then we have psi T of alpha being 1, 1, 0, since there's one small lowercase a, one lowercase b, and then there's no c's in alpha. And then alpha sub/t is equal to AB, because it's only considering the terminals within alpha. So now let's move on to another definition. Let us define another concept, which is the step function. So given alpha and beta, which are elements of V union T star, so this means they're words which are constructed from both non-terminals and terminals, we're going to let the power set of alpha beta be the set of productions of G that can transform alpha into beta. To formally state this, what it's saying is P of alpha and beta is equal to the set of all transitions, well, basically the set of all capital A goes to gamma, which are element of the rule, the set of rules are, where there exists alpha 1 and alpha 2, which are both words constructed of non-terminals and terminals, where alpha is equal to alpha 1 A, alpha 2, and beta is equal to alpha 1 gamma, alpha 2. So what we can see here is that it's the set of all rules which transform in capital case A, so a non-terminal A, into another non-terminal gamma. And if this set is not null, then we call alpha beta a step which is denoted by alpha goes to beta. So now, after these definitions, let's go into how we construct this NFA from the CFG. So let G equal to the four-tuple V, T, R, and S, where V is the set of non-terminals, T is the set of terminals, R is our set of rules or productions, and S is our start state. We'll also define lowercase n to be the number of non-terminals in the CFG, and let K be greater than or equal to 1. We now will define the K Parikh automation of G as the NFA M sub G of K, which is equal to a five-tuple of Q, T star, delta, Q0, and the set of final states, and is defined as follows. Alright, so now let's talk about what Q and T are defined as. So Q in the NFA is the set of all states. So within this, we're going to define the set of all states to be all n to the n vectors under certain restrictions. We say n to the n here because it's basically vectors of size of the number of non-terminals, so the magnitude of V. And these are x1 through xn. We have a certain restriction here, which is the sum of all the elements within this vector should be less than or equal to k. This is because technically you could continuously, within a CFG, keep on producing more and more non-terminals without reaching the terminals. And this would not be possible within an NFA because the vector would become increasingly long. So for this, what we've done is we've ensured that xi, the sum of all elements, should be less than or equal to k to limit this depth. And then we have T, which is the alphabet, which is simply gotten from the CFG, as that's a set of terminals. So now let's go into the definition of delta, which are the transitions in the NFA. As we stated previously, Q is a set of states which are Parikh vectors. So what's happening here is we take a Parikh vector, and then by doing a transition, which is based off the terminals that are added in the CFG, we then reach another Parikh vector state. So this is basically stating that if we have alpha and beta as two words in the CFG, if we take their Parikh vector, only considering the non-terminals as one of the states, and then we have gamma, as we defined previously within the step, and we only look at its terminals, if we use those two, we then reach a new state, which is psi of V of beta. And this state exists, this transition exists for every valid step, where psi of V of alpha and psi of V of beta are states in the NFA. So after we defined Q, delta, and T, we now need to talk about Q0, which is our start state. This is quite simple, because it's basically psi V of S, where S was the start state in the CFG, and now we're just taking its Parikh vector. And now let's define QF, which are the final states of our NFA. This is basically only one state, which is psi V of epsilon, which is all zeros. This is because when a CFG terminates, there are no more non-terminals, so their count should be 0. So we should only have terminals in the word that the CFG terminates on. Therefore, we have shown that we can construct an NFA from a CFG with this very clear definition of Q, T, delta, Q0, and QF. So now that we've shown that a CFG can be converted to an NFA, we also need to quickly show that an NFA is also a subset of CFGs. This is quite a simple proof, and we've shown it in class. We can see this since an NFA is basically just a PDA without a stack, and we know that PDAs are equivalent in power to CFGs. Hence, NFAs, irrespective of Parikh image being applied or not, are subset equal to CFGs, since they're a subset equal to PDAs. So now, in conclusion, we have shown that we can go from an NFA to a CFG, and we can also reduce a CFG to an NFA under Parikh's image. Hence, we have proven that they are equivalent in power with this construction. So now let's do an example construction of an NFA from a CFG. Let us consider the following basic CFG, which is S goes to S capital B, or A, and then capital B goes to B, capital B, A, capital B, or C, capital S. We can now construct a 3-Parikh automata. Since I said 3-Parikh automata, this means that our K here is equal to 3. Now the states are all pairs x1, x2. These are pairs because if you consider the number of non-terminals we have, it's just 2, which is S and B. And we also are under the restriction that x1 plus x2 should be less than or equal to 3, since this is a k-Parikh automata where k equal to 3. Now let's consider the transition 0, 2 goes to, under BA, 0, 3. And we can explain this as follows. We apply a production B goes to B, capital B, A, capital B, to a word with 0 occurrences of S and 2 occurrences of B. And now this leads to a word with 1 new occurrence of both B and A, as well as 0 of S and 3 of B. If you look at the top right, you can spend some time analyzing how this NFA actually meets the requirements of this CFG. For example, it starts at the correct start state, which is 1, 0, since there's only one S. And then under an epsilon transition, so this means that no new terminals have been added, we can go from S to SB, and then we reach the state 1, 1. Furthermore, all the rest of the transitions make sense in this 3-Parikh automation.
So now we will talk about the significance of Parkh's theorems, specifically the applications of Parkh theorem. And within this explanation, we will include examples as well as explain some necessary terms involved to understand the concepts such as periodicity and holomorphisms, which is important to help us obtain an understanding of Parkh's theorem. So now we will talk about every CFL over a unary language which is regular. So given a CFL over a unary language, say sigmas of A, for Parkh's theorem for any context-free language L, we know that there is a regular language R such that psi of L is equivalent to psi of R. So these languages L and R are letter equivalent. Since the CFL has no ordering due to the fact that it is over a unary alphabet, and there exists a regular language whose Parkh's mapping is equivalent to a CFL, then the CFL itself must be regular language, which we'll discuss further in detail in the following slides. So another fact that we must mention is that a unary language that corresponds to an eventually periodic subset of natural numbers has a predictable behavior. And this is important for our case in terms of Parkh's theorem because this allows them to be recognized by simpler computational models such as final automata and other computational machines. And as a result, we know that if a language is not periodic, it is neither context-free nor regular. So how do we prove a language is not context-free? Well, to show that a language is not context-free, we must show that the language is not context-free for all grammars, in this case the automata. So let's remember that a set S of the natural numbers n is periodic if there exists a natural number n0 and period p greater than or equal to 1 such that the natural number n is greater than n sub 0. So we have a natural number n and a set S that if and only if that the natural number n plus the period p is also in the set S. So this subset corresponds to a unary language we had defined in the previous slide, which actually eventually has to be periodic due to the Parkh's theorem. So in this case, these natural numbers could be 7, 8, 9, 10, and then 7, 8, 9, 10 repeats again, 7, 8, 9, 10, with p representing the gap between the repeating natural numbers. So under the Parkh's theorem, we should also be able to, for L, apply the homomorphism matching both letters to alpha, which we also referred to on the previous slide for unary languages. So homomorphism is defined as a function that maps strings from one alphabet to another. and this allows us to preserve the structure of a language. And a function f from s to s prime is holomorphic if f of a times b is equivalent to f of a times f of b for all a, b in the set S. So basically, if you multiply a and b then apply x, you receive the same result as first applying x and then multiplying a and b. An example is shown below for our language using induction to show n to n plus 1 for those two cases. And we can see that after simplifying this particular language, there's an arbitrary long gap between the languages, and thus 2 to the n squared plus 2n for natural numbers n greater than or equal to 0 is not eventually periodic. So because it is not periodic, like we had mentioned in the previous slide, L prime is not regular nor context-free. So now we will talk about Park's theorem made symbolic by a hack in 2023. So the usage of Park's theorem in string analysis involves determining if the strings of x are accepted by y. So we know that we can use Park's mapping to encode a language as a small linear integer, and these examples could include abstract context-free languages or abstract strings of numbers. And attached below is two links that provides us the full paper explaining Park's made symbolic by hack, as well as the full video on YouTube that will allow us to better gain an idea of this. And now we will delve into the references in the following slides. Thank you. Here are references for our presentation, and this concludes our presentation on Park's theorem by Kevin Lin, Andrew Zake, and Srisankaet. Thank you guys for listening.